You tell me when to start.
Okay. Okay, you can start.
Okay, so this is the welcome to this event. It's the last one before the summer. Next time we will convene toward the end of September, and the next event will be devoted to experimental particle physics. Now I'll let my colleague Andrea Malchiodi introduce our speaker, who I would like to thank for accepting our invitation. Thank you.
Okay, thank you, and especially thanks to Sylvia. So I will introduce her. So Sylvia is a renowned expert in partial differential equations and mathematical physics. And she works in particular on Ginzburg-Landau theory of superconductivity and statistical mechanics of Coulomb-type systems. So she was a student at École Normale Supérieure in Paris and got her PhD in Orsay under the supervision of Fabrice Betuel. And so she started as an instructor and a CNRS researcher at ENS in Cachan. And then she was assistant professor, associate, and professor at the Courant Institute in New York. Then she spent some years in Paris at Paris 6. And now she's back to Courant as a silver professor. So she has had several distinctions. It would take me a while to mention all of them, so I will just make a small selection. So she has been a member of the Abel Prize Committee recently. She was elected to the American Academy of Arts and Sciences. She got a Simons Investigator Award. She was a plenary speaker at the International Congress of Mathematicians in Rio in 2018, and also plenary speaker at the European Congress of Mathematics. She got the Henri Poincaré Prize and the European Mathematical Society Prize. So she supervised several students, and she's also involved in editorial work. So she's one of the founding editors of Probability and Mathematical Physics, and also editor in several renowned journals like the Journal of the American Mathematical Society, Communications in Pure Applied Mathematics, Asterisks, and many others. So it's a pleasure to have Sylvia to speak about the system of points with Coulomb interactions.
Okay, thank you very much. Thank you for the kind invitation and for the kind introduction as well. It's a pleasure to speak in virtually in the Scuola Normale with such a broad and diverse audience. So I want to talk about, as the title says, systems of points or particles, which have in common that they have a Coulomb-type repulsion or singular interaction more generally, but we will see exactly what we mean. So remember the Coulomb interaction in dimensions 3 or even higher is 1 over the distance between particles to the power d minus 2, if d is the dimension. And in dimension 2, it's a bit particular. It's a minus log of the distance. So of course, up to a multiplicative factor. So it's always repulsive. So I will consider now that I have n particles or points with these interactions. I will add the sum of the pair interactions between points, little w here, and possibly add some extra potential energy, where V here is some potential that's chosen to be sufficiently nice and to grow sufficiently fast at infinity. So the idea is that if you don't add any confinement potential, it's called, then because of the repulsion, the particles can just fly off to infinity. So you will not have a minimizer of this energy, for instance. So the n sum v of xi is there to counterbalance the effect of the repulsion and keep the system in a sort of finite size box. This is why you have a balance on the left. Left term is of order n squared, and the second term is also of order n squared. Okay, so I talked about Coulomb interaction. I will also consider some slight generalizations. One is to consider the logarithmic interaction, but in one dimension, where it's not Coulombic. So this is called also a log case, a log gas. Or another one is to consider general inverse powers of the distance, so still repulsive, but general powers. And that's called the Rees case. I will refer to this as the Rees interaction case. Okay, any questions so far? Feel free to interrupt. I can see you, so it's good. All right, so what kind of questions are we interested in asking? I would say mathematical questions. One, for instance, is to study minimizers of this energy. Of course, we want to let big N go to infinity, the number of particles. So what do minimizers do? Another possible question is to study evolution equations, so systems of ODEs that are well coupled, of course. So here I wrote the gradient flow corresponding to the situation where you take the velocity of the particle I equals to the average of the gradient, minus 1 over n, minus the average of the gradient of the energy with respect to the position of the particle I. So that's the gradient flow, but it's in a sort of mean field regime, what it's called, which is that each particle feels an average force generated by the other particles. And then Newton's law, which is the physical one, corresponds to the acceleration of particle I equals to the average force exerted by all the other particles. Right. So again, you want to understand the limit as n goes to infinity. And a third type of question is to study states with temperature and do statistical mechanics. So I will mention that towards the end. Okay, so why these systems are interesting, I will give you just a brief review of motivations. First motivation is not from physics, it's from approximation theory. So here you want to find points that are good interpolation points. So, you know, let's say you have a function f, which is regular, and you want to approximate the integral of f on a surface or in a Euclidean space. So how should you approximate this integral? By a discrete sum. So in other words, which are good interpolation points that will give you a small error? Well, it turns out there is a theory for that, these best points, the ones that give you the least error, are called Fekete points, and they turn out to maximize quantities like this here, product of distances. So that's if you're in a manifold which is closed without boundary. You just want to maximize products of distances, but maximizing product of distances obviously is the same as wanting to minimize minus log of the product of distances. And minus log of the product is going to give you minus sum of log of the distances. So you are actually trying to minimize a logarithmic interaction energy. And these problems arise also with weights, where you have here, you see these weights, exponential weights. If you take the log of this, again, you will find that you're trying to minimize exactly an energy of the type that I wrote in the logarithmic interaction case. So there is a large literature on this in the approximation theory community. And I lost my picture, but okay. So more generally, what people do is that they also consider general inverse powers of the distance. They call that the Rees S energy, and they try to minimize this on again on closed manifolds. This provides a whole one-parameter family of problems, right, where when S goes to 0, formally, you recover the logarithmic interaction minimization. And when S goes to plus infinity, formally, and even rigorously, you recover the best packing problem. So the interaction becomes very short range. And it becomes the question of packing, you know, the maximal number of hard spheres in a given volume. And this is the solution in 2D that I wrote here. You want to pack your balls according to a hexagonal or triangular lattice, as you can see. Okay, so what's going to happen is that you will have a macroscopic distribution and a microscopic arrangement of the points at a scale that's depending on n. So I will show that on pictures. Okay, second motivation comes from condensed matter physics, and Andrea mention that I had been interested in the theory of Ginzburg-Landau of superconductivity and also superfluidities, Bose-Einstein condensate. So this is where this comes from for me personally, which is that you want to understand in these models from condensed matter physics, you want to understand PDEs, in fact. So in these PDEs, you have an unknown, which is a wave function, if you want, a complex valued function. Here is written psi. And it solves a certain elliptic equation here, Ginzburg-Landau, in a case that's time independent. So I wrote the simplest version without gauge of this model, but you can do it with gauge, it's the same. Okay, and then you can have time-dependent versions, for example, the parabolic Ginzburg-Landau equations or the Gross-Pitaevsky equation, which is the Schrödinger version. And in these models, what you're interested in is the zeros of the wave function psi, the complex zeros. So there are topological objects, they come with a topological degree. And when epsilon goes to 0, the characteristic length scale of the vortex goes to 0. So epsilon is a length scale here. It's related to the Ginzburg-Landau parameter in physics. It's the inverse of it, in fact. Okay, so what you can do is you can rigorously analyze these PDEs or these variational problems with tools from calculus of variations, etc. It's like phase transition type problems. And at the end of the day, what you prove rigorously, and this was the work of many people mentioned here, you prove rigorously that everything happens as if these vortices were really just discrete point charges with logarithmic interaction. So in fact, you can forget about this whole PDE and you can reduce to a discrete problem that I mentioned at the beginning in 2D with the logarithmic interaction. So the 2D Coulomb system or Coulomb gas, or also called one component plasma in physics. Okay, so such problems also arise in 2D classical fluids with the point vortex systems that you may know of. Okay, so in this model from superconductivity or superfluidity or blah, what we have in addition is we have experiments and they show us very nice observations on vortices that you see these vortices arrange themselves forming these beautiful triangular patterns. So this is called the Abrikosov lattice in the physics of superconductivity. Abrikosov was the physicist who first predicted from the Ginzburg-Landau model that such periodic patterns should arise, and then they were observed. Okay, so this is where I wanted to say there is going to be these microscopic patterns, which are these triangular lattices, and this micro scale, which is the distance between two vortices, very small. It's n to the power -1 over dimension, right? So if you have n points in a fixed box, the typical distance to the nearest neighbor is n to the -1 over d. So that's going to be the micro scale behavior, but it's going to be also a macroscopic behavior, which here is a uniform distribution of points. Okay, the third motivation comes from statistical physics and quantum mechanics, and it's a motivation for looking at states with temperature. There are many instances where you encounter these Coulomb gases, these log gases, in particular cases that come from random matrix theory. So it turns out that if you take the simplest random matrix theory models, you want to take a very large matrix and you want to draw the entries at random. So the simplest thing you can do is to make them Gaussian IID. Right, so all the entries follow the same law. The law is Gaussian. Then you can compute the law of the eigenvalues. And what is the law of the eigenvalues? Well, it exhibits a logarithmic repulsion. It's telling you that basically the eigenvalues repel themselves logarithmically. They don't like to be too close to each other. If you assume that your matrix had some symmetry, were symmetric or Hermitian, then the eigenvalues will be forced to be on the real line, and you will get a logarithmic gas on the real line. But if you don't impose symmetry, you will get points in the complex plane for your eigenvalues, which will behave just like a 2D Coulomb gas. So that's a particular motivation for studying 1 and 2 the logarithmic cases. There's other problems from quantum mechanics, in particular the fractional quantum Hall effect, where you see these Coulomb gases arising, or these one-component plasma, physicists call them. And also, the Coulomb gas is a sort of classical model for matter. So it's a well-known model from statistical mechanics, which is sort of relevant when you want to model stars in astrophysics. And in any case, it's always been important as a theoretical model. Another thing that's important is the case where you consider logarithmic interaction in 2D, but you allow two types of particles, particles pluses and particles minuses. You know, you have opposite charges, and then you allow for not only repulsion, but also attraction. So minuses attract. This is related to other important models from theoretical physics, the XY model, the sine-Gordon models, so all these models in which you see Kosterlitz, Thouless, phase transitions, etc. So many motivations from, let's say, from theoretical physics in general and statistical physics. Okay, so now I want to go back to my question of understanding these distributions of points as n goes to infinity. So first we're going to try to discuss the macroscopic distribution and then the microscopic distribution, as I was trying to describe before. And at the same time, we want to also understand the asymptotic expansion as n goes to infinity of quantities such as the minimal energy. For instance, if you're in Fekete points on a sphere, you know, these things that maximize product of distances, there is a conjecture that you can expand the minimal energy in powers of n, but also with powers, but also some n log n terms and some log n terms. And the coefficients in these expansions are unknown. It turns out that the coefficient A here, which is the leading order term, is quite easy to compute. This second term with n log n is also not hard to guess by scaling, but all these other coefficients, B, C, D, are completely unknown. And now what we have access to at the moment is we can give access to the coefficient B, some characterization of it, or at least the fact that it exists, but beyond is completely open. Okay, so this is a type of questions. It turns out that answering this question, expansion of the minimal energy, is directly related to understanding the first two questions, even though it may not appear at first. Okay, so first order of business is to understand the mean field limits. What are the limits for the distribution, the average distribution of particles when n goes to infinity? So the way we do it is we form the empirical measures. So you have your particle xi, you put a Dirac mass at each particle, divide by the number of particles, and try to see if this has a limit as n goes to infinity. Okay, so I rewrite here the energy, the type of energy that we are studying. It turns out that this has a fairly easy answer, known for many years. It's sort of classical things related to potential theory. So the equilibrium, the empirical measure is going to converge to something called the equilibrium measure, something that's uniquely characterized. Mu sub v, let's denote it like that. It's a probability density. And the minimal energy is going to, once you divide it by n squared, is going to converge to E of mu sub v. And what is E is in red here. Okay, so what is E? It's, if you want, the sort of continuum version of the interaction energy. So you take the same interaction, but now you do it for probability densities. You add the same external potential V, but there is no N anymore. And the other difference is that you don't worry anymore about removing the self-interaction of the particles, because you know W, remember W is a Coulomb type or Rees potential. So at the origin, it's always plus infinity. W of 0 is always infinite. So you don't want to count W of xi minus xi, because that would be infinite. You have to remove it. But here, you don't care. you can put back the diagonal because you are going to consider, in fact, densities mu that don't have Diracs, that don't concentrate. Okay, so now this energy E is strictly convex, and as such, it has a unique minimizer. And that's unique minimizer. That's what's called the equilibrium measure, or the Frostman equilibrium measure. Okay, so if you look at minimizers, you will have a completely determined limit, which is typically unique if you have good properties on V. If you want to be a little bit careful, you have to make sure that this is integrable. The kernel W is integrable near the diagonal, and that will force S to be strictly less than D, where S is the power. You know, the W is 1 over X to the power S. So this power has to be strictly less than the dimension for this integrability to hold. All right. So what do we get for equilibrium measures? Well, there's a few cases where we can compute them explicitly. An important example is the case where the external potential V, confinement potential, is quadratic. That's an important case because it corresponds to Gaussian things. In all Coulomb interaction cases, then you find that the equilibrium measure is an indicator function of a ball. So it's a uniform density in a ball, properly normalized to be a probability. Okay, so that's called the circle law in random matrix theory, and it's telling you that your particles are going to distribute themselves uniformly in some disk. That is the effect. This is the resulting effect of this repulsion together with this quadratic confinement. So the particles stay in a fixed set and eventually equilibrate to a uniform distribution. If you also consider the quadratic confinement but a logarithmic interaction in 1D, then it's a famous result that the equilibrium measure is this thing, the semicircle law, which is the measure whose density has a graph that follows a semicircle like this. Okay, so it's supported in a fixed interval. So that also is well known to appear in random matrices. So these are the types of measures we think of. You know, something nice, something that has a compact support and that has a nice density on its support, sufficiently regular on the support. I use the same notation for the measure and for its density. Okay, so I want to say a little bit, but quite briefly, about the dynamics questions that I posed at the beginning. So when you have a distribution mu, think of it as your limiting distribution of charges or something, you can form the potential generated by mu. So W being your kernel, you can form the convolution of W with mu, or something I call H mu, which is just this, Wx minus y d mu of y. So if W is the Coulomb potential, this is the, sorry, it's the Coulomb kernel, then this is the Coulomb potential. And the mean field, the total mean field potential here is going to be H mu plus V, this external potential. So H mu is the self-generated potential, if you want, and V is the external thing. And what are the particles going to feel? Well, they are going to feel the mean field force, which is minus the gradient of this. So what you can expect, and formally it's not difficult to derive it on the back of an envelope, is that, for example, if you take the gradient flow evolution, you know, xi dot equals minus gradient of the energy divided by n. The limiting density mu, which is the limit of the empirical measures when n goes to infinity, is going to solve some type of evolution equation, a PDE, which, well, a PDEist would call a continuity equation, that says that dt mu is divergence of this force, the opposite of this force, times mu. So if you've never seen an equation like this, what this is saying is that you have a density, and this density is going to be moved or transported with velocity field equal to this, basically this minus gradient blah, equals to the force. Okay, if you have generally just a Dirac mass that's moving, the time derivative of the moving Dirac mass is minus divergence of the velocity times the Dirac mass. This is a general fact in the sense of distributions, if you want. So that's the analog of this, not for the Dirac mass, but for the sum of all Dirac masses, so for the average density, if you want. Okay, so you want to solve you're going to eventually have to solve this PDE with initial data corresponding to your initial limiting density. And now the difficulty is to pass to the limit as n goes to infinity from this discrete ODE system that's written here. So this is what we're talking about here, this gradient flow system, to this PDE, this evolution equation that I wrote it in red. So even though you can guess it, it's not easy to derive it. Everything is very nonlinear, and you have the singularity of the interaction. So I will just mention that it can be done. You have these difficulties, you had some previous results, limited to some certain non-too singular interactions, I would say, or low dimensions sometimes. But now you can prove it for Coulomb interactions and for interactions with powers even worse than Coulomb. So from d-2 to d, as long as the power is integrable and it's super Coulombic, then if you start from the solutions to this ODE system, you can prove convergence of the empirical measures to the solution to that limiting PDE that I wrote before. Okay, the convergence will hold for as long as you know you have a good limiting solution. So as long as your PDE is well posed and has a nice enough solution, I don't want to get into too much detail. So there's some recent improvements on this. We can now do more general cases. And the other thing maybe I want to mention is that I obtained similar results for Ginzburg-Landau dynamics, for these PDEs that I mentioned before that are parabolic or Schrödinger-like. You can actually go straight from these PDEs to equations of this form, which in this case take the form of fluid equations. So just like here, you can recognize Euler in vorticity form can be put vaguely in that framework. You can get fluid equations from quantum fluid models in a way, like those for superconductivity and superfluidity. Okay, so I will say a word about the technique when I move to the next slides. But so far we've discussed average distributions, the limit of the empirical measures. So I want to emphasize that none of these results were really so specific to Coulomb. In fact, they were for regular interactions, something smooth, no problem. You have an equilibrium measure. You can do these things for dynamics, everything. It works for Reese interactions that are more severe than Coulomb. So it's not really specific. So after this, I'm going to start using really properties that rely on the Coulomb nature and their interactions much more specifically. And what is specific to Coulomb is that Coulomb is the fundamental solution to the Laplacian, as you know. And the Laplace operator is a very nice operator, kind of the best differential operator that you can have. In particular, it's local. It's a local operator, right? So if you take any other kernel, which is not Coulomb, you can always make convolution with that kernel, but it's the kernel of an integral operator, which is not local in general. You can view it as a Fourier multiplier if you go to Fourier, but it's not going to be a local differential operator in general. And so we're going to exploit the fact that the Coulomb kernel satisfies this property. Okay, so to be more specific, as you know, Coulomb solves this PDE minus Laplacian W equals Dirac at the origin, up to some multiplicative factor, CD. Okay, so now if I talk about my Coulomb potentials, they solve h mu that I wrote before. They solve a local elliptic equation, as I said, minus Laplace h mu equals mu, or up to constant, or a Poisson equation, if you prefer. And so now we can start looking at quantities like this. So if you have mu and nu, think of them as two probability densities. You can define this square norm, this sort of square Coulomb norm, to be this double integral of wx minus y, mu minus nu of x, mu minus nu of y. So it's kind of the total Coulomb interaction of the distribution mu, viewed as a positive charge distribution, and the distribution nu that would be viewed now as a negative charge distribution because of mu minus nu. Okay, so you could also rewrite this with convolutions, and now you can rewrite it as h mu minus nu, the potential generated by mu minus nu, multiplied by mu minus nu itself, which is just up to factors minus Laplacian of this potential. Okay, so now when you have the potential times the minus Laplacian, you are tempted to integrate by parts. You want to use Green's theorem, and you transform this into an integral of gradient h mu minus nu squared. So now it becomes, instead of a double integral, it becomes a single integral, but in terms of the potential. So it becomes a sort of natural energy quantity, the gradient of the potential squared, which is like the Dirichlet energy, but of the potential. So now we can start to think of things locally and to sort of view the energy as some sort of extensive quantity, except we have to go via the potential. So it's not via mu itself, but it's via the potential. Okay. So in order to prove the convergence of the evolution equations that I was mentioning before, in fact, what I do is I use this thing as a distance. This becomes like this Coulomb distance becomes a good way of measuring how close your empirical measures are to the limiting solution that you expect. And you can prove a Grandval relation on this distance, that the derivative of it is bounded in terms of itself. And this is what does the trick. This is going to be now also used a lot in what I'm going to describe afterwards. And I mentioned it works for Coulomb, but you can make it work with a little twist for these Riesz kernels with S between d minus 2 and d. So, okay, it's not exactly the kernel of a Coulomb of a local operator, but you can make it into a local operator by a trick of dimension extension that I don't want to mention. Okay, so now we're going to start discussing next order expansion for the minimal energy, because I told you the mean field limit is described via the leading order. So the leading order of the minimal energy is n squared times the energy of the equilibrium measure. At the next order in Hn, you will find some information on the microscopic distribution of the particles. Okay. So what is going on? 1 second. Is that we're going to start describing the difference between the fluctuations, the difference between the Diracs and the equilibrium measure that we want to understand. All right, so main idea is we want to take the equilibrium measure, we want to expand around it. So we want to make this difference, right? Difference between the Diracs minus n times the equilibrium measure, and form the potential Hn that's generated by this difference. Now, with the trick that I described just before, you can rewrite the energy after you expand around mu v. So, you know, the energy is going to be the energy of mu v. That's the leading order thing. It has an n squared in front, plus a next order term. And the next order term I can rewrite is as the integral of grad hn squared with this little trick that I tried to explain here. And this next order energy now is expressed in this sort of local way I explained that allows to use a screening procedure and compute the energy additively. Okay, I don't have time to go into too much details. But so now what we're going to define is a limiting next order energy for the patterns at the microscale. So you're going to have a picture like this. This is the support of the equilibrium measure. This is the microscale. And these are the blow-ups of the configurations. So you want to take your configuration and zoom everything by mu v of x times n to the 1 over d, so that the limiting density, the density of the particles becomes 1. So you normalize everything, you zoom everything, so you expect to see 1 point per unit volume, roughly. Okay, so these are blown up configurations that you could observe, this green one, this red one, this blue one. And for each of them, you're going to define an interaction energy, a total Coulomb interaction energy, W, which is going to be the Coulomb interaction of these Diracs at these points, blue points or red points or green points, and the interaction with a negative background, which is the effect of this minus n mu v. So when you zoom, this becomes like a uniform background. And you can normalize to be of density 1. So it's as if you had a negative background of charge -1 all the time, -1 per unit volume. And that's called a gallium in physics. And now you compute this total W energy. I will not give you a precise definition, but and what you have to do after that is you have to sum, or you have to average over all the blow-up centers. So when you zoom near this green cross, you see one configuration, you compute its W. When you zoom near this red cross, you see another configuration, compute its W. And then you have to sum over all possible centers. And this average, or this sum, is denoted W bar. So now, what is the result? The result is that in all these cases that I described, logarithmic case or Coulomb case or Riesz case with between d minus 2 and d, you can expand the energy of a generic configuration as a leading order term which is fixed, which we have seen before, n squared times E of mu v. Then a light blue term which is there only in the logarithmic cases, so it's there by scaling. This is also fixed, plus a next order term, which is n to the power 1 plus s over d times W bar, where W bar, as I described, is this total energy of all these blown up configurations that you obtain from the initial configuration. Okay, so at next order now, in this W bar, we start to see a selection principle. If you want to minimize the energy, because everything else is constant, well, you should minimize this W bar. And so what this tells you is that the microscopic patterns formed by the points should minimize something. There is a variational principle again. They should minimize this W, which I didn't fully define for you, but trust me, there is a definition. Okay, so after this blow up, you should minimize W. So this works for all these interactions. It also worked for Ginzburg-Landau vortices directly from the Ginzburg-Landau model. And then we can start to describe these point patterns. And one of the things we prove is that if you minimize this W, you have to be very well distributed. In a certain sense, you have to be equidistributed. So this is the best we can do. But now I'm going to tell you a bit more. So what are really minimizers of this W looking like? I remind you that formally W is Coulomb interaction or Riesz interactions between positive Dirac charges together with this negative background charge that's neutralizing and keeping everything together. Okay, so if you're in dimension 1, you can show, because everything is normalized to have density 1, right? Because the background is of density 1, so there should be always 1 point per unit volume on average. The minimum of W will be to put the points on the lattice Z. So you put the points exactly periodically. It's not so hard to prove, it's like a convexity thing. But now what happens for higher dimensions is much more subtle. So there is something called the Coulomb-Gas conjecture, which is much broader than this question, but this conjecture says that there are some special dimensions, 2, 8, and 24, for which you have some special lattices, and in dimension 2 it's the triangular lattice, which should minimize a very broad range of interaction energies. In fact, all interaction energies which are completely monotone. Okay, so all interactions for which the interaction is decreasing and its derivative is increasing and its second derivative is increasing, etc. That's what they call completely monotone. That includes also sphere packing, etc. So they conjectured that for smooth interactions, but what we proved with Mircea-Petrake is that if you can prove their conjectures, then you also obtain it for the Coulomb interactions that are not smooth, for the Reese interactions, etc. So it means that if the conjecture is true, then the triangular lattice must be minimizing this W energy, and E8 lattice in dimension 8 would be the analog, and Leach lattice dimension 24 would be the analog. And now there is a big breakthrough that you may have heard of, which is that this conjecture was solved in dimensions 8 and 24 by Kohn, Kumar, Miller, Radchenko, and Vyazovska, following the breakthrough of Vyazovska on the sphere packing problem in dimension 8. All right, so it's a sort of follow-up of that work. So in dimensions 8 and 24, we have an answer as to what the best configuration of points is. It is a lattice, and it is a special lattice. In dimension 2, it's still a conjecture. In other dimensions, it's probably not always a lattice. In particular, if you're above dimensions 10, 11, for large dimensions, minimizers should not be on lattices. Dimensions 2, the only thing we have still is this conjecture, but as I showed you, we see these triangular lattices in the Abrikosov lattice observations in superconductors, and we were able to derive W rigorously from the Ginzburg-Landau model. So this is a sort of proof by experiment that this conjecture should be true. The other thing we have, which is a very partial result, is that the triangular lattice is the best among lattices. So that's a number theory result, which is actually has been known since the 50s, which compares all lattices of fixed volume and finds that the triangular lattice is the best. So in particular, W sees a difference between a square lattice and a triangular lattice being better. In dimension 3, for instance, BCC is expected to be the best lattice or the best configuration, but it's not even proven that it's the best among lattices. So these are difficult questions, which are actually of number theoretic flavor. But yes, always very difficult, these types of crystallization questions. There's very few positive results, I would say. So now how long do I have left? Because I have no watch, so I'm a little bit out of Andrea.
I guess, I don't know, about 6, 7 minutes, but you can take a little more. So.
All right, so I will discuss in the time left the situation with temperature. I mentioned it arises in random matrices, quantum mechanics. So what do we want to do there? We want to consider Gibbs measures, where now we assign a probability to configurations. The probability is proportional to exponential minus beta times the energy of the configuration. We have to normalize by something that's called the partition function, which makes this into a probability density. Okay, so configurations with large energy now will be less favored, but this has to be carefully weighted and measured. A quantity you want to understand, for instance, is the free energy, -1 over beta log of the partition function. And again, there's some conjectures as to an expansion, just like before, in powers of n and n log n. And the coefficients in these expansions are unknown, but are of much interest to theoretical physicists. In particular, they have even geometric interpretations. Okay, I don't want to spend too much time on that. So at leading order, you still find again this equilibrium measure. So, you know, the average distribution of points, the empirical measure is going to resemble the equilibrium measure, except with exponentially small probability. But now, if you want to look on the left and on the right, you will see the effect of temperature in the microscopic distribution. So on the left and right, distributions are still uniform in a disk, which you know from the equilibrium measure being, you know, the circle law, uniform in the disk. And on the left, you have low temperature, so large beta. So, you know, beta is the inverse of temperature. So beta being large means temperature is small. Beta being small means temperature is large. And so when temperature is larger, you see the configuration is kind of more shaky. And I'm going to illustrate it again here as we're going to decrease temperature. And you see the configurations being more ordered and less shaky, while the average distribution is still the same, the macroscopic or mean field distribution. Okay, until maybe at the end you believe you will converge to a triangular lattice or something like that. Maybe. Okay, so to express what's happening with temperature, we need to describe it in terms of point processes. Here are two pictures of point processes. On the left is the Poisson point process, what you obtain when you throw your points kind of uniformly at random. And on the right is the Gini point process, which is the point process that comes out of scaling limits of these random matrices, you know, where I told you draw the entries to be Gaussian IID. Well, these eigenvalues, they repel each other logarithmically, and this is the only case where you can compute explicitly the point process. You see it's much more rigid than the left-hand side. Okay, so what we proved with Thomas Leblé is a large deviations principle in the language of probability, but you don't have to worry too much about that language if you don't want, which is again valid for all these log or Riesz interactions with powers between d minus 2 and d, which is saying basically that now it's no longer that you want to minimize W like it was for energy minimizers, but now when you have the Gibbs measure, it concentrates on configurations which minimize something else. So it's the point processes Px that minimize now a sum of W, some average of W with respect to Px, and a relative entropy. Okay, so let me slow down. So what is Px? Px is the point process centered around X. When you zoom around X, you see a point process. Now you have to average over points X that vary in the support of the equilibrium measure. So this is the average W, this Coulomb energy. And the right term is the relative entropy of the point process with respect to the Poisson point process. Okay, so if you don't know relative entropy, here is actually a specific relative entropy. Roughly, it's like a distance. So it measures how close your thing is to the Poisson point process or how much it resembles the Poisson point process. And so now you see that what you want to do is you have a variational principle. You want to minimize something where you have a complete W and entropy. And when beta is very low, well, the entropy term can be neglected and you just want to minimize W. So that corresponds to very small temperature. You're back to the situation of low temperature states of minimizers. So just wanting to minimize W. So maybe you get crystals in low dimension. All right, at least in dimensions 1, 8, and 24, you do. And when beta is very small, on the other hand, it's very large temperature, then it's the entropy term that matters. And then you want to have the entropy small, which means you want to resemble the Poisson point process. So when temperature is very large, you converge to the Poisson point process. So all this makes a lot of sense. And in between, you have a competition between energy and entropy. And you see these patterns that have a little bit of, you know, a bit shaky, but still a bit rigid. And there are many questions that are open in theoretical physics, in particular to understand whether there are some phase transitions for fixed beta in which the behavior would vary, would sort of change rapidly, abruptly, in particular in terms of decay of correlation functions. But I don't have time to get there. Together with this result, we obtain an expansion of the free energy, where, as I said, as I announced before, we can now access the term that's in factor of n, and the coefficient in front of n is directly related to the minimum of this function. So it's the sort of new achievement to get there, but everything that's beyond, we don't know. And we can prove the existence of limiting point processes up to subsequences. And maybe to finish the talk, I want to give you just one last result, which is that we can prove something finer about the fluctuations. So you know how you have the sum of Dirac's minus n times mu v. We expect this quantity to actually be relatively small. But it's even better than that, because if you take a test function f, which is smooth, so this is in 2D, a result in 2D. If you take a test function which is sufficiently smooth and you test it against this difference, so this sort of fluctuation measure, if you want, not only this thing is much smaller than n, but it's actually of order 1, so it actually has a limit without normalization. This thing converges to a Gaussian distribution with a certain mean, which is explicit, a certain variance, which is explicit. And you don't need to normalize. So it's not like a usual CLT, you know, when you have IID random variables, you need to normalize by 1 over root n to converge to a Gaussian. Here it's a non-normalized quantity. And the fact that it still converges means that everything is very non-IID and everything is very rigid in some sense. And this can also be obtained on localized scales, etc. So if you are a little bit familiar with probability, there is a limiting object behind this associated to this convergence, which is called the Gaussian free field. And the reformulation of this theorem is that the potential generated by this distribution of charges that's here, the inverse Laplacian, if you want, of this, converges to this Gaussian free field, which is this very, very rough two-dimensional sort of surface described here. Okay, so now I conclude. I hope I've convinced you that the analysis of Coulomb systems is interesting by being at the crossroads of many questions, of course, of physics and mathematics, but even within mathematics, many branches of it: analysis, PDE, probability, number theory, geometry. There is a collective macroscopic behavior which can be understood by mean field theory. So this is these equilibrium measures that you can describe. But then if you want to understand the microscopic behavior, what you do is you expand the energy to next order. And you get to these questions of minimizing W, which leads you to crystallization questions and conjectures. An important tool was to phrase the energy in terms of the Coulomb potential generated by the configurations. And then, thanks to that, things become local and additive, and you have these screening procedures that I didn't have time to describe. And the approach also works with temperature and shows that you have these Gaussian limits, you know, Gaussian nature of the fluctuations, and that things are actually much more rigid than you could at first expect. And also, you get this variational characterization of the limiting point processes, where you see the competitions between order and disorder. And finally, one question I feel always remains in this business is how much of this is really specific to Coulomb, or even Reese interactions. Like we use the Coulomb nature in the proof, but how much of the phenomena would persist for very general interactions or monotone interactions? What do you really need? I don't know. So thank you for your attention. Sorry for going a little bit over time.
Thank you.
Yeah, thanks, Sylvia, for the great talk. You really showed many interesting connections. Are there any questions?
I have one curiosity I would like to satisfy myself about. When you talked about the packing problem, essentially, Then you mentioned 8 dimensions and 24 dimensions.
Mm-hmm.
Now, there's another intermediate dimension that I would have expected to play a role, 16. And the reason is that that 8-dimensional E8 lattice has modular properties like the 24-dimensional case, which is related to the monster group. And the 16-dimensional case plays an important role in string theory because there are 2 lattices. One is the lattice, the so-called E8 cross E8 lattice, and the other is the spin 32 over Z2 lattice. They also have modular properties, and I would have expected that 16 dimensions something special happens, but just based on what happens in 8 and 24, I don't know. How come?
But you're saying there are 2 lattices then in 16 dimensions?
Yes.
2 interesting lattices.
Yes.
Yes.
You mean there could be the competition between those cases? Because yeah, that's a good point.
Yeah,
yes.
That's the point, I think. The conjecture says that
it's not a unique choice. Yes.
They want a universal lattice. So
yes.
It has to be the best for all interactions. So if you have 2 in competition, probably.
Yes. But they could be interesting phenomena with 2 things that you could have some sort of resonant behavior between the 2. I think the 16-dimensional case could be very interesting to analyze. I understand that not being unique, you have this problem, but having 2 solutions may have other phenomena in store. So it's.
I'm sure, yeah. Every case is interesting to analyze, and this probably is a good starting point of an interesting dimension. But yeah, this is a question for the number theorists, honestly. But
Thank you.
Any more questions? I wanted to ask something. So when you introduced the model with temperature, you mentioned some geometric, terms with some geometric interpretation in the expansion. Can you just say a couple of words?
Yes. So I didn't have time to get in there. But, okay, so what you can do is you can decide that you're actually on a manifold instead of being a flat space. Right, and you have a metric, and then the metric on the manifold is sort of the equivalent of the V, the external potential. So changing the metric is like changing the V, it changes the equilibrium measure, it changes everything. And so then the coefficients that are in the expansion, you can express them, at least formally. There are some conjectures by these theoretical physicists, that the coefficients can be expressed in terms of the equilibrium measure explicitly in dimension 2. And now if you re-express them in terms of the metric, they become quantities that are well known to geometers. In particular, the entropy, the integral of mu log mu is called Mabuchi in this context.
Oh, I see.
So you get the Mabuchi functional for the leading order term, and then you get the Liouville functional for the next order term, which is an integral of grad log mu squared. I mean, you have some explicit forms like that, and then you get also an Aubin-Yao functional.
I see. Okay.
So for people who are used to working with metrics, this is these are natural objects, natural geometric quantities.
Okay, yeah. In fact, yes, as I expected, maybe some conformal invariance if you use exactly the Coulomb potentials.
Exactly.
Yeah.
But I worked only in dimension 2. In dimension 2, you have the conformal invariance of the log, so things are very particular, and that's the only dimension in which there are explicit conjectures like this.
Because in general, you need to modify the Laplace operator. It's not the Laplace operator which is conformal invariant, but you have like the conformal Laplacian. So you might need to introduce some scalar curvature to get the conformal invariance. So
yeah, obviously a direction of all this is you can start to do these Coulomb gases on manifolds and to replace W with the Green's kernel of your manifold, and you can start playing the same games, finding the equilibrium measures and the microscopic distribution. So some of it has been done already, but some of it needs to be adapted. It's not completely obvious to adapt, but it's also a natural setup, and apparently it's also physically motivated, so it's not just a geometric curiosity.
Okay, thanks. Any more questions? Okay, doesn't seem to be the case. So I guess we can thank Sylvia again for the wonderful talk and for having accepted our invitation.
Thank you very much. Take care. I hope to see you again for real one day.
Real.
Thank you again. Thank you again. Bye.
Bye-bye.
Thank you. Bye.